So good afternoon. So we are starting lecture 40. In the last lecture, you remember I just at the end, I introduced the concept of hot carrier induced effects, or sometimes also called hot carrier strays. Hot electron or hot carrier strays in a MOSFET. I told you then when the MOSFET size is very small, it goes to micron to submicron to deep submicron region, particularly this channel length. When it shrinks to values less than 1 micron, then for practically any voltage applied, maybe several volts, the electric field in the channel, particularly at the drain side, becomes very high. It easily exceeds the value about 20 kilovolt per centimeter, making the carriers to travel in saturation with saturation velocity. That means these carriers become hot. The average energy of these electrons moving at that very high velocity, corresponding to a field exceeding 20 kilovolt per centimeter. So the average energy of the electrons becomes more than that of the lattice, and we say the carriers are hot, hotter than the lattice. Actual self, I told you earlier, physically it does not mean the temperature increases, but the carriers we say, because the average thermal energy is represented by kT by Q, or in general 2/3 kT or 1/3 kT by Q per degree of freedom. I think you know that. So it is energy is a function of temperature. The so-called temperature of electrons we say is more than that of the lattice temperature, and such carriers are called hot carriers. Please note they are actually not hot physically. These hot carriers means highly energetic carriers. They travel along, in this case of our electrons, they will travel along the field lines but opposite to the direction of the electric field. And at the edge of the drain, at the drain edge where the electric field is very high, some lines will shrink and that will penetrate through the ultra thin oxide, get outside. And typical lines of force near the edge at the drain end looks like this. So electrons move like this. Okay. As a result, some of the electrons tunnel through because of the high energy. Some of the hot electrons tunnel through the oxide, may reach the gate, and again maybe tunnel back to the drain. In that process, some of the traps, bulk traps, as well as the interface traps in the oxide get filled up with electrons. And as a result, the threshold voltage changes. Threshold voltage changes mean the current voltage relationship changes. So ID value for the particular VD and particular VG for which it was designed, that ID value may change due to this effect, which is called hot carrier strays or hot carrier induced strays, or we call it hot carrier deterioration, hot carrier induced failures, and various names are assigned to that mechanism. This is particular for specific to the ultra small transistors, miniaturized transistors, because any reasonable field of the order of a few volts will create a very strong electric field, compelling the carriers to move at a very high velocity. And because of the strong field, hot carriers are generated. And secondly, because of the strong field and ultra thin gate oxide, the tunneling probability is also more. Because of this combined effect, okay, that some of the states, bulk traps as well as the interface traps in the oxide get filled with electrons, causing a shift of the threshold voltage, and hence causing a change in the IV relationship of the MOSFET. It's a permanent failure or temporary failure. After a long time, the failure may be restored, but gradually the failure takes place, and ultimately there is a permanent failure of the device. To overcome this problem, which is very, very important, this problem is very, very prominent in submicron MOSFETs. People conceived an idea which is normally called LDD MOSFET or light doped drain MOSFET. It's called LDD MOSFET. LDD MOSFET, before I go to LDD MOSFET, I think I should discuss briefly how a modern MOSFET is fabricated. That will give you an idea, and then automatically the LDD concept will come. Let us see that how a modern MOSFET is fabricated. Initially, you do some, that is called a process called local oxidation, by which, of course, before local oxidation, you do an implant which is called field implant. The first step is field implant. Field implant means in the region outside the transistors, the space which is otherwise not occupied by the MOSFETs, those areas of silicon, they are implanted with a relatively heavy dose of boron. This is p-type silicon. I am speaking of NMOS. Similarly, you can extend it to CMOS technology. So, referring to NMOS technology, starting with the p-silicon substrate, you define a mask by which you cover the regions in which the transistors are located. Say, for example, from here to here, it is covered by a mask, maybe a photoresist mask, maybe an oxide mask. Then the remaining region is implanted with some relatively heavy dose of boron at an energy typically around 50 kilovolt, typically, or sometimes 100 kilovolt. It has to be designed properly. Thereafter, by a process called low-cost process, local oxidation process, local oxidation of silicon. Local oxidation of silicon is a special process by which you grow field oxide, which is reasonably thick, much thicker than, at least 5 times thicker than that of gate oxide. And this is normally called field oxide. Okay? So these regions, and below which we have a number of boron ions, that means negative acceptor ions, and that was introduced during the field implant process. That will remove the inversion layer from other regions, so that the different devices on the substrate did not get connected. Otherwise, the presence of an inversion layer may cause a very poor electrical isolation between the MOSFETs on the chip. I told about it in the last class, and I mentioned several occasions, on several occasions. Then what you do some implantation of phosphorus or arsenic through a certain mask, so that you get a region like this. This is N plus. So using the mask number 2, using the second mask, you cover the silicon and only open these regions, and through the windows in the mask, you implant. This is called source drain implant. source and drain are defined by the process of implantation, of course it is followed by some anneal. Implantation must be followed by an annealing process. Okay? Thereafter what we do, after this process, we grow carefully a very, very thin oxide. This is what is called gate oxide. So over the entire surface, you grow a very thin oxide. Okay? I'll not show the steps, so next is gate oxidation. This gate oxidation usually is chlorinated. Why chlorinated? I also mentioned earlier, because of the presence of sodium ions, which is abundant in the nature, there will be some high degree of ionic conductivity in the oxide. Similarly, the sodium ions accumulate either at the silicon interface or at the top by the voltage applied, and which causes a shift in threshold voltage. And that is what is known as threshold instability caused by sodium ions. To immobilize sodium ions, therefore, we do oxidation in the presence of chlorine. Chlorine forms a compound with sodium and immobilize them. Okay? That's how you reduce the effect of threshold instability caused by sodium ions. So this next process, next to source drain ion implant and anneal, you grow the gate oxide, which is ultra thin in modern MOSFETs. It's ultra thin. Thickness may vary from about 100 angstrom to about 300 angstrom, depending on the technology. Even below 100 angstrom oxide thickness is also being used today in research scale, in R&Ds. Okay? Thereafter, you deposit a polysilicon film. Next is polysilicon. Now, oxidation normally you can do without any mask, because this field oxide is very thick, and ultra thin oxidation on it does not matter. So oxidation stage you may not use any mask. Okay, but then polysilicon deposition, that also is maskless. After polysilicon deposition, you use a mask to define the gate electrode. So this is polygate definition using mask number 3 perhaps. In fact, I am not interested to discuss the technology in detail, but I am bringing in technology because I have never discussed technology in the class. I thought let me discuss a little bit, briefly about the technology, and automatically the LDD concept comes in. That's why I brought it. So you do polygate definition by a lithography. So ultimately what is happening, you are getting here a polysilicon gate looking like this. And just below it, there is an oxide. Okay? I am not showing the oxide here. Please remember, there is an oxide here. I am not showing intentionally. There is an oxide here. Everywhere there is an oxide, thin oxide, gate oxide. On the top, you deposited a polysilicon film. Usually, you deposit it by using the LPCVD technique. Low pressure chemical vapor deposition technique, LPCVD, or low pressure chemical vapor deposition technique. In all photolithography, please remember, we use normally not chemical etching, but an etching called RIE, reactive ion etching. Please remember that is the technique, because we are making ultra small dimensions. So you cannot use ordinary chemical etching, which gives you a lot of undercut, and definition becomes very difficult. Therefore, you do a vertical etching called anisotropic etching using a technique called reactive ion etching or RIE. That has to be remembered. Today's MOS technology, nobody uses the chemical etching technique. All RIE or reactive ion beam etching. Yes. Okay. So after the polygate definition, what do? You please see that there is a thin oxide everywhere, ultra thin gate oxide. Then we deposited polysilicon by LPCVD. We have defined the polysilicon by photolithography and some good etching technique like RIE, reactive ion etching. Afterward, you grow a CVD oxide on the whole thing. This is called CVD oxide. That means deposition. It's called CVD oxide means, I should not have said CVD oxide, oxidation, but CVD oxide. CVD oxide means deposition of CVD oxide. Oxide, silicon dioxide deposition by chemical vapor deposition. It is done using silane, SiH4, and oxygen mixture, cracking at a low temperature around 400 degrees centigrade. If you take silane and oxygen and crack it, chemically react it at 400 degrees centigrade, silicon dioxide is deposited. Okay? And this silicon dioxide, which is deposited like this everywhere, that is of much thicker value. It is rather easy to grow a deposited thickness of around 2-3 micron without much difficulty by CVD process. Whereas if it is growth process, oxidation of silicon, it takes a lot of time, but you get a better quality oxide. Okay? But in this case, intentionally we use a thicker oxide with a good good coverage like this. I can show you here, not on the main design. So I told you that there is a thin oxide, then there is a polysilicon, which has been defined by photolithography and reactive ion etching. Then you grow or rather you deposit a thick oxide by chemical vapor deposition technique. This is the gate oxide grown thermally. It is a chlorinated oxidation. Then on which you are growing another oxide, but this is a deposited oxide, not a grown oxide, and that is a CVD oxide. I am showing this part, but intentionally I am not showing all these things here. But I want to show the final diagram here. That is why. So CVD oxide, then do some reactive ion etching. That means you bombard on it some reactive ions like fluorine ions, usually fluorine ions or fluoride, that's SF6, either using CF4 plasma, C2F6 plasma, SF6 plasma, sometimes a mixture of fluorine and chlorine. There are various techniques. You do some ion etching. So ion etching, what will happen as a result? Gradually, ion etching removes molecules from the surface. But you see, effective thickness seen by the ions in this region is much more than in this region or in this region. The thickness seen by these ions here is this much. Thickness seen by the ions here is this much. It is the same because you have grown the same oxide everywhere. But thickness seen by the ions here is double. At the edges, because there is a conformal deposition, this thickness is double the thickness of the film deposited here, here, or here. So what will happen? When the etching is just over, and when this polysilicon surface just appears here, and normally this thin oxide is extremely small. I have not been able to show it in scale. Whereas this thickness is about 3 micron or 2 micron or 1 micron, this thickness may be some 200 angstrom, which is negligible. I cannot draw it in scale, but I have to show you. I have drawn it in scale. I have tried to show it. So when this oxide is removed, automatically the thin oxide below it also is automatically removed. You cannot have any control. Do you know what will happen at the end? You will get a very interesting kind of thing which I want to draw. No. This is the ultra thin gate oxide. From here to here, this is, I am not maintained at all, try to maintain scale. This is the ultra thin gate oxide whose thickness is around 200 angstrom, 150 angstrom. But on the sides also there is an oxide. This oxide of course was deposited CVD oxide, and the lateral thickness may be say 1-2 microns. These, you understand what has happened? Oxide has been removed from this region, oxide has been removed from this region or this region, but from this region it is difficult. So ultimately what will happen? Partly the oxide will be removed, but something like this will remain here. Something like this will remain here. This oxide will be removed. These are called sidewall spacers. These oxide films at the sides, they are called sidewall spacer oxides, SPACER. Sidewall oxide spacers. Okay? After following this, you do some heavy phosphorus implant. High dose phosphorus, not very high dose, about, it depends on the technology. In very modern ones, the energy may be around 50 keV, but in the old days it was about 100 keV. But relatively high dose of phosphorus implant may be around 10 to the 14 to 10 to the 15 per centimeter square. Do you know what will happen as a result? Just here, there will be an N plus layer deposited. That is by the ion implantation. Because phosphorus, you may use arsenic antimony. Today, of course, nobody uses phosphorus. People use antimony implant, high dose antimony implant. So what will happen? From here to here, it will be a mask against the implant. Whereas from here to the remaining region, there will be some implant. In fact, you can keep this region covered. Let us not complicate this region. But I'll be coming to that. You can keep this region. Usually this, up to this, it is covered. But this region may be. Similarly, the PMOS which is kept here in the NOL, if it is a CMOS technically have to be kept covered. I'm not going to the details of that, okay? So what you have done? You have done some antimony implant so that you have a very, again have used a very exaggerated scale. Okay? This is a very thin N plus region created by antimony implantation. And implantation being a highly directional process. Okay? The age of the implant will be almost coincident with little bit, there will be very little encroachment. But otherwise it will be almost very precisely aligned with the edges of the oxide walls. Thereafter what you do? You have to do considerable annealing, because just implantation will not help. Because implantation causes lot of damages. Implantation, the impurity atoms mostly are interstitials. Unless you anneal, you cannot restore it from damages. You cannot achieve the electrical activity of this material, doped material. Okay, so you have to do some high temperature anneal. And this high temperature anneal does two things. One is definitely it restores the damages, restores from damages. it restores the electrical activity, but then it also causes some drive-in diffusion. So as a result, what happens? Ultimately, you get a profile which looks like this. And you critically adjust the antimony implantation dose and energy and anneal time such that this region doping is relatively less than the doping of these regions. Is it okay? Whereas the doping here may be of the order of 10 to the power 20 to 21 in this region. Doping may be around 10 to the power 20 to 21 per centimeter cube. In this region, doping is around 10 to the power 18 or like that per centimeter cube. So you see that what we have done, the so-called drain, which is very heavily doped, has been extended with a lightly doped drain, whose doping concentration is about 2 to 3 orders of magnitude less than that of the actual drain, the contact, where the contact is made. Similar things happen in the source also, does not matter. Let me tell you, automatically it is a process technology, is called self-aligned gate technology, gate process. Automatically gate is defined. You don't have to use a second technique for aligning the gate with respect to this channel. Automatically the gate is defined with respect to the channel. But at the same time, by using this technique, I am creating a lightly doped region in this side and in this side. But in this side, really, it does not cause much difference. But it is in this side, the drain side, it plays a very, very important role. So what is the next step is, I have forgotten to write. After CVD oxidation, you do RIE, reactive ion etching, to produce oxide sidewall spacers. Then what you did? You did some antimony implant, which makes the polysilicon N plus, as well as this region also little bit N plus, not that N, concentration has to be adjusted properly. Then you do some kind of doping. Polysilicon, you know that doping does not matter much because oxide diffusivity is very low. So polysilicon dopant will be redistributed and will remain almost, the polysilicon resistivity will not change much. Whereas there will be appreciable redistribution of impurities in this region. There will be lateral penetration also. Diffusion is a isotropic mechanism. Diffusion takes place not only vertically but also laterally. So as a result, you see that what has happened, this from here, the edge has spread over to exactly below the actual gate. Polysilicon ranges from this point to this point. This is very important. Okay? Thereafter, what you do, after this, so we have created the so-called lightly doped drain MOSFET, LDD MOSFET. Okay? Thereafter, do you know what they do normally? You see that these sizes are extremely small. Films are extremely thin. So as a result, the sheet resistances of these films are very relatively high. And then the line resistances also very high. So very high means appreciably high, and that causes appreciable RC delay. To reduce the RC delay, what you do, we silicide the contact. What do you do? You just deposit a titanium, usually a titanium film everywhere. Titanium film, titanium deposition. Sorry, before that you did anneal. Then titanium deposition. Everywhere deposit titanium. okay, and then react it at a high temperature. Do you know what happens? Over this region, titanium gets converted into titanium disilicide. Here also titanium gets converted into titanium disilicide. And on this also titanium gets converted into titanium disilicide. However, on oxide it does not happen so. Of course, there is a nitridation. I am not going into the details of that. What I say that after titanium deposition, you heat treat it at a temperature around 900, 950 degrees centigrade in a certain atmosphere. Before that also something else is done, okay? And as a result, silicidation takes place, reaction takes place. So silicon exposed region, either silicon or polysilicon, gets converted into silicide. Polysilicon converted into silicide is called, usually in the language of technology, we call them polyside. The polysilicon converted into silicide is called polyside, whereas the silicon converted into silicide is usually called simple silicide. That's how we differentiate between the silicide on polysilicon and silicide on crystalline silicon. It's the usual technological terms. But over this region, there will be no silicide formation. Over this region, there will be no silicide formation. On oxides, there will be no silicide formation. Silicide formation will take place only on polysilicon and silicon. I think you anticipate what will happen as a result. You will find that there will be selected silicidation, but excepting the regions which are covered by oxide. Then you wash it in a certain acid. The titanium which is unreacted is removed. This particular orthophosphoric acid boiling and all these things are done. So the titanium from unreacted regions is removed. Do you know what is going to happen as a result? Over this is a very interesting thing. There will be a titanium silicide here. There will be a titanium silicide here. There will be a titanium silicide here. Then do metallization. You deposit aluminum film on it and take contact like this. For example, this becomes drain. Your aluminum, this is titanium. The green one, okay? Then you deposit aluminum everywhere and define the aluminum electrode is called interconnect formation. Titanium is called contact formation, self-aligned contact formation. And then you deposit tight. You know that gate is very narrow here, but then gate thing comes sidewise, then goes on the laterally, it moves and then comes on the thick oxide, the field oxide, from which you have to take contact. Similarly, from directly you can take contact from here for drain and source. To connect the drain with something else and this source something else if necessary. And for that, the normal vehicle of metallization is usually aluminum or usually aluminum silicon alloy. A little silicon is added with aluminum, and nowadays aluminum, silicon, and small amount of copper. Okay, so what happens at the end? You see, it's very interesting. You get a thing like this now. This is the aluminum, and this is your drain, on which directly you do not deposit because it is so thin that you cannot do lithography here, because this has to be done by using a certain mask. You are depositing aluminum, defining it using a mask. So you have to use a mask here. Okay, and you cannot have, because it is such a, what is the length of this now? Maybe 0.18 micron for its 0.1 micron CMOS technology. You cannot have a lithography on 0.1 micron. You cannot have the registration accuracy. So what is done, if you have to make a contact of this gate with something else, what you have to do? This gate comes like this, then it goes above the field of sight. It becomes thicker. This electrode becomes a little bit bigger, on which you deposit the aluminum and connect with the other thing. That's how it is done. That is why I'm not showing you the contact. This becomes simply gate. And similarly here, this is your source substrate, usually common. And normally the substrate is grounded. Normally the substrate is grounded. So, you know that quickly I have given you an overview of the basic technology which is used. I think one thing I have missed. Can you tell me which one I have missed in the whole thing? Huh? The mask is, it depends on, some cases mask is photoresist mask, sometimes it is oxide mask, sometimes a metal mask, various kind of, but here, if you are using a photolithograph resist mask, you don't have to do any other deposition. Just you deposit a resist and define it. It acts as a mask. It depends on the implantation dose. If it's a very high dose implantation, high temperature process, don't use photoresist mask. Then you have to use an oxide mask or nitride mask, and all this different detail. But I have told you that I have missed a very important thing which I have discussed in the class.
What is the benefit of this antimony deposition?
Antimony?
Antimony implantation.
It is a self-aligned process. Automatically the gate is defined. You don't have to do a separate alignment for defining it. Because self-aligning. I'm asking you a very specific question. Which step I have omitted and I should not have done so? Because I have discussed it in the class. It's called channel implantation. You have to do some channel implantation. That is done. Can you tell me when the channel implantation is done? Just like I have to do some channel implantation. When you will like to do the channel implantation? After the gate oxidation. So just here, I have just forgotten a step called channel implantation. Following the gate oxidation, you do channel implantation. Thereafter, you do the other things. It's a very complicated thing. Whole process has to be simulated. Otherwise, you cannot do it. Now, if you have understood the basic technology for making an ICE, for making a MOSFET,
So the substrate and this layer is directly connected with no substrate is.
Sometimes, which I have normally done is here. I just forget to tell you. There is a boron implantation here also. Usually, a boron implantation is made for a good contact, which I forgot to tell you. So many masks are there. It may be a typically 12 masks to 18 mask process. Though the simple technology may require only 6 masks, but there are so many things added. And as a result, the number of masks, photolithography steps is quite big, quite a very large number today. And therefore, we have to do everything as best as possible by self-aligning techniques. It's not going to the technology because otherwise it will consume the whole class. Because that implantation is usually, that if you do not, if the ion beam is a directed beam, parallel beam, and silicon being a crystal, as ions are entering, they see a lot of channels, open spaces. The atoms are very nicely arranged. In certain directions, you find almost hollow spaces called channels. So the ions penetrate unnecessarily quite deep, and there is uncontrolled implantation. This is called channeling effect. To avoid that, 2 things are done. Either you implant a thin oxide. In that case, ion beam gets scattered. So direction, the channeling is reduced or practically stopped. Or do implantation a slight off angle, about 3/4 degree angle. these things are there. Therefore, it is customary to use channel implantation following the gate oxidation. There are many things. My important thing is the LDD. How the LDD MOSFET, now I think you understood why I have discussed this technology. I think you have definitely have understood, because I introduced the concept. I said that this is a problem of hot carrier stress. Then I said the problem to a great extent may be solved by making a lightly doped drains MOSFET. Then I said that because lightly doped, we have never discussed the technology in this class, I found that because the LDD MOSFET is automatically created in the modern technology, I give you a very brief overview of the technology. Now let me explain what LDD MOSFETs does. So if you now see properly, what I have done actually, you have made a device like this in the drain side as well as in the source side also it is like this. Whereas this is N plus, this is N, this is N plus, this is N, and this is your oxide, and somewhere here you have your gate. And modern technology is such that the overlap is very small. The positive, there is a need for a little positive overlap, but that can be controlled precisely to almost 0 plus. Let me tell you, mathematically almost 0 plus. It is possible to make it very, very small. Now, because now what will be the shape of your so-called diffusion depletion layer? Will it be like this? Just sorry, I'm too much making. If I draw the depletion layer due to the drain bias like this, do you have any objection? You see, what has happened? Sorry, it will not be like that. Sorry, almost like this. The depletion layer within this, within the N plus region, what will be the depletion layer contour? This is the depletion layer, sorry, within this channel, more or less like this. Whereas within the doped region of the drain, the depletion, because here it is low doped, depletion layer will be wider. Here it is highly doped, depletion layer will be very thin. Near the surface, because it is low doped, the depletion layer will be wider within the drain. Whereas near the bottom region, it will be very thin. Whereas on the other side, it will not be affected much. There will be a little effect, but not much. So as a result, what is going to happen? The overall depletion layer width from here to here is widened. As a result, the electric field will be reduced. Am I correct? And if electric field is reduced, you are producing less energetic carriers. And also because of the, that electric field lines will be like this only now. Otherwise, there will be very steep kind of electric field lines. There will be electric field lines due to the fringing effect. But it can be shown by proper simulation. The electric field, not only near the surface, not only it is reduced, but the penetration of electric field is also to a certain extent reduced. Two things happen. One is, because of the widening of the depletion layer, the electric field is reduced near the surface. And secondly, the electric field penetration through the oxide and back, that is also reduced slightly. But because the electric field value is less, so what is going to happen? Tunneling probability is reduced, and hot carriers are also not that hot. Carriers are not that energetic. So the hot carrier induced stress will be reduced. The defects or failures due to hot carriers will be minimized. And that is what LDD MOSFET is. You see, in the source side, this does not help. In fact, nothing happens. There is no need to make in this lightly doped source here. But the technology is such, it automatically happens, but that does not affect the performance. People have done a lot of simulation to show that the lightly doped source, so-called, does not really create much problem. Whereas lightly doped drain, the drain side, makes a lot of advantages, particularly from hot carrier point of view. Hot carrier induced stress is appreciably reduced because of the lightly doped drain structure. It is a very, very interesting device structure. People have done a lot of work on it. That because of the complicated profile, etc., you cannot analyze such structures by analytical methods. You have to definitely go for numerical techniques, solving 2D equations, Poisson's equation and current equations and continuity equations to determine the property of the. Therefore, you have to take help of say simulators like Minimos or MOSIS or SPICES. Minimos, originally it was very famous. There is a simulator called MOSIS. Then there is a simulator called SPICES. It's a combined bipolar MOS simulator. These are all 2D simulators. These are all 2D numerical simulators. To analyze these structures. Okay?
So, okay, after field observation, we went in for a channel implantation. What did we followed an annealing